Hello, everyone. My name is Nathan, otherwise known as Own Man Builds. We have the Benny Factor here today. We also have Sean Calderon, or like he calls his channel, the Mad Coiler. What's going on, guys?
Doing great. Nice to see you guys.
Yeah, good to see you.
We should have Gerald joining us in a little bit, but guys, Sean made it back.
Yeah.
Hey, everyone. I missed you guys, and it feels so good to be back.
Well, it's good to have you back, Sean. We missed you, buddy.
Yeah.
Thanks, guys. It means a lot. So much.
Yeah, Ben's got a big announcement, and he's been gracious to allow me to go first, and then he's going to let out the secret.
Awesome.
And he keeps teasing it to Sean, and Sean's waiting patiently for it.
I know. Can't wait.
Yep. In a little bit, we'll tickle that Elmo, but for now.
Tickling his elbow with high voltage. I saw it last time.
That's funny. My goodness.
Oh, so I thought with all the stuff that we're doing with the Tesla coils, guys, that we'd go ahead and take a look at where Sean and I were doing it at first. In our first experience in trying to put this together and find out exactly how to put a ZVS Tesla coil, we pretty much watched the same videos in all the Tesla coil builders out there who did it. And they're not real explanatory on this stuff. They don't explain a whole lot. They like to tell you that they did it. And some try to explain it, but the main part of this is how you build the number 2 coil. And without that, a ZVS Tesla coil is an absolute failure. Trust me, I have video footage of mine smoking constantly.
I remember those videos. Awesome.
All right, Ben, you got the chat. I'm going to go ahead and do a little presentation for you guys, and we're all going to chime in, all right?
Sounds good.
Oops. Sorry, I'm fiddling with buttons here.
Oh, you're good.
No worries.
Okay. Now, we all started off with this ZVS right here. This is the one we wanted to use for this project. This is the one that everybody else was using. It just required a change in capacitors in order to make it work. And different people have different ideas on the capacitors of this.
Yeah.
So we go to the next one. Very simple. This is what Sean sent me. He said, Nathan, I got you on this. I know exactly how to build this thing. Let me help you, right? And I thought, all right, here we go. Maybe, maybe not. We'll see. We never knew Sean was such an expert in the field. So,
Nathan, could we go back to the first slide you just shared real quick?
Yeah, absolutely.
There we go. So this is the ZVS as Nathan described. You can purchase them on Amazon. They're not too expensive. But what you're looking at is it's a low frequency oscillator. And what that means is that positive and negative waves run through that copper coil. And as they move through that copper coil, those positive and negative waves, you can put something in the middle. Like, let's say if you want to test it with a screwdriver tip, you can put it right into that coil, and then it'll start to get hot. And so that's what's called an induction heater. But what Nathan and I decided to do is turn it into a oscillator for a Tesla coil.
Nice.
Well, it seems like it's the right fit, right, Sean? So what you have is 2 MOSFETs, and they're just turning on and off like switches. So it turns on one, then it turns on the other. So it seems like, if something pulses, then we should be able to make it into something that does a Tesla coil, because all we got to do is pulse the primary, and the secondary will take on the signal, right?
That's correct. And when you show in the next video us removing all those capacitors, those black things, the 6 of them there, more capacitance means a lower frequency. We don't want that for our Tesla coil. We want high frequency. So we're going to take off those capacitors and add our own capacitor. And as we lower that capacitance, then that pulse you were talking about increases. and therefore we can pull out the power out of the Tesla coil.
I just want to stop and recognize how adorable that circuit is. It's so awesome. It's sleek. It's, dare I say, a sexy circuit.
It is. I really believe there's an aesthetic quality to electrical circuits, and they're half art, half science to me. And I'm not sure. I thought I was the only one that thought that way.
No. I am right there with you. It's a nice looking design. Kudos.
So the next step in this is adding capacitance. Okay. This is where Sean started to throw me for a loop. I'm not used to adding capacitance to things. I didn't understand it. And here he is with 6 capacitors, right? And every video I've seen, they have 1 or 2 capacitors.
What's the rating of those capacitors?
They are 470 nanofarads. So what you're looking at, there's 2 different ways to connect capacitors. You can connect them in parallel, or you can connect them in series. These are connected in series. When you connect capacitors in series, it lowers the capacitance. So instead of the 6 capacitors, the black ones that I made note of in the earlier slide, those were in parallel. They were to be added to create a large capacitance, which means a low frequency. These 6 white capacitors are connected in series. Therefore, it's a very low capacitance, which brings up the frequency.
Yeah, something to learn, an entirely different subject. Meanwhile, just so you guys know, I cram course this in about, 30 days, Sean, or less, in exactly how this stuff works?
You did. You picked up on it real quick, a lot quicker than I did.
So here's Sean showing off. So when he told me he had it, he did.
This was my first breakthrough, so I was pretty excited. And if anybody is ever tinkering with these kinds of circuits, it takes a bit of learning curve. I guess it takes a little bit of endurance, because there's so many failures. And so when you hit a win like this, it's a lot bigger for the experimenter.
Yes, it is. Oh,
For sure.
you can't just do that. Was AC, by the way. So it was a loop Sean was going to throw at me later on in the entire thing. By the way, if you can see it, just look right behind on the oscilloscope, and it shows you the ring frequency in this thing.
Yeah, I see that on the O-scope. That's crazy. And look at those arcs. They're insane.
Yeah, you'll notice that they're sword shaped, and that's the shape you'll get with AC on this kind of coil. This is 3.5 inch wide. I'm sorry, 3.5 inch diameter, about 9 inches of PVC pipe wrapped with 34 gauge wire. And so as the AC comes in, the negative part of the AC is taken away by the diode, and only the positive part can come in. And so that positive hump, when it hits as an input power, it sort of adds a burst of energy every time. And that burst shows up in those swords, or that sword-like shape.
Nice. And then he went on to show it in DC.
So DC is what's called a quasi-continuous wave. And so you'll see that it doesn't have those large sword type arcs, but it's sort of this smooth, fluffy ball of plasma. And so that's how you kind of tell the difference between DC and AC as the input. AC will have the swords, and DC will have this sort of fluffy ball of, it sort of hisses instead of the crackling that the AC has.
So one of the biggest things too is you always get the sparks with the AC. With the DC, it pushes out the field so that you'll get a very long distance to light up your light bulb.
It's a good point. You're totally correct on that. It seems like the AC pushes out more of its energy, whereas the DC sort of stays within the sphere of its power, and then, like you said, it has more of effect at distance.
So this is my pathetic attempt to start to build this coil. I just used the number 2 coil that I had. I didn't have a breakout, so I flicked the little Batman symbol I had and just threw a wire through it.
You did great.
Sean had to be laughing, to the bank with this one when I showed it to him. And I just wound some coil for the number 1 coil. And I'm trying my hardest. I just didn't know any better, guys. So here we go. I even lit it up with a DC battery.
That's awesome.
That's very crafty of you. That's cool. I would never have thought of using the battery pack from my electric screwdriver.
For your drill, huh? Yeah. So
yeah.
As you can see, my capacitance is different as well. I had 1.50 nanofarads on each one. Put them together, which gave me half of that. So I got 0.75. So you're not adding them, you're dividing them when you get into this.
Yeah, that's a good point, Nathan. When you connect them in series, you're dividing them. And when you connect them in parallel, you're adding them. So those two 150 nanofarad capacitors in series cut in half gives you 700. Wait a minute, 75 nanofarads. Oh boy, am I missing something here?
I don't think no 0.75. Yeah,
0.75. Yes. Okay.
Yes. No, so I did this wrong, by the way. If you look at it, Sean tells me to put the switch onto the negative side.
Mm-hmm.
So here I go putting it on the positive side. I didn't know any better.
Yeah.
So I'm thinking this is positive and break the positive. That's what we do. That's not how Sean's mind works. He breaks the negative.
Yes, and whenever you're using a DC source like this, you always need a switch, because if you don't have the switch, then the voltage and the current will sort of ease into the circuit and it won't oscillate. So using the switch lets that voltage and current build up. And so when you flip the switch, then you have this quick rush of voltage and current, and it kickstarts the oscillations.
So here it is, my coil again. And here's Sean. Now, this is a special coil, Sean, if you want to tell him about it. But this is one he pulled up on me, and I didn't know what it was.
Sure, Nathan. This is a 4-inch tall coil, about 1.5 inches wide or in diameter. And I put some grooves into the 3D printed cylinder there. That allowed me to wind way more copper wire than you could if you just use like a PVC pipe without grooves. And then what happened is I submerged it into a two-part epoxy and put it in a vacuum chamber. In the vacuum chamber, it removed all the bubbles, so the epoxy was very clear around the coil. And so what I was able to do is now push a lot more current, a lot more voltage into this little coil to get larger arcs. So that's basically a quick explanation.
Yeah, it's like an AC flyback, but as a Tesla coil.
Yeah, that's a good way to put it. If you've ever seen the coil of an AC flyback, you'll see that it has a bunch of turns of wire, then a divider of plastic, then a bunch of turns of wire, and then a plastic divider. This is the same principle.
Okay. Here's Sean correcting me on how to fix it and put the switch on the negative side instead of the positive side. There was a lot of this, by the way. I pointed out, and it's funny now, But I had so much wrong with my coil when he first showed up. It was unbelievable. Like everything I did was backwards compared to the way Sean does it.
You, you, you did fine. I had spent days on this, so I had to jump on you. So no, you were picking it up pretty quick. I just took a bunch of pictures. And by the way, Nathan and I didn't know each other. It was more of I left some comments on his YouTube channel saying, "Hey, I'm doing something similar." And then I sent a bunch of pictures and videos from my phone. Nathan just does a really great montage, turns it into a presentation. And that was our first video.
Yeah, that was pretty funny. I'll show you guys a little clip of that video later, and you'll see me burning things up. You'll find out why everybody tells you I fry it and find out.
I love it. Fry it and find out. Hey, Nathan, can we take a quick second here to look at the comments?
Yeah, go for it. Which one you got?
Awesome. So forgive me, guys, if I'm a little slow on catching up, but I see here from QUOUD10. I'm sorry, I can't pronounce that. So it asks the question, what do you think would happen if you 3D printed a V shape instead? I'll be giving you a demonstration of a cone that I'm winding. Maybe that's what you're referring to. And if not, I'll check the chat. But interesting question. Thanks for sharing.
Very good. And what's going on right here on this slide is Sean's just telling me take the wire that comes from the number 2 coil. It's your ground wire. So you have to keep it away from the ZVS circuit itself because you do not want to interrupt it and cause like a mixed signal or something. Is that right, Sean?
Correct.
So I went ahead and did that. This right here is probably the biggest learning. Okay, so let me take a minute to break this down. Sean and I needed to build a coil. We had seen all the coils. He had his specialty coils that he already tuned. I had mine that wasn't going to tune right because the resonance frequency was in the 700s. So we had to find out the frequency of the ZVS itself. Every time we tested the number 1 coil, the number 1 coil had a frequency range. So the range at the very bottom was in the 500 kilohertz. At the very top, it was in the 200 kilohertz. So we had to come up with a number 2 coil that actually put us within that resonance frequency. So I suggested to Sean, let's split the difference. Let's find something that resonates at about 300 kilohertz. And then we need to find a computer program that actually will allow us to do this. So we went to Java TC, so Java Tesla Coil, and we started punching in numbers. And I'll give Sean all the credit in the world on this. He figured out actually how to make this thing work.
Yeah, I appreciate that. This software is really good. Unfortunately, it's very complicated. And it's only intuitive to, I think, the Tesla coil person who's built many Tesla coils. And so what this basically tries to do is if you put in certain values, it'll spit out the answers you need. For example, I want to wrap this coil at this size with this wire, and then it will tell you, oh, you need this capacitor. Or if you're looking for, like as Nathan said, I want a particular frequency, then we start changing coil 1 and coil 2. And we start changing the diameter, we change the number of turns, we change the wire gauge. And as we start to change these variables, it spits us out our dimensions of how to build coil 1 and coil 2. And so Nathan, once we figured this thing out, Nathan then designed a coil, secondary coil, to the dimensions of what this program spit out. And do you have that coil, Nathan, to share?
I do. It's coming up.
Okay. Yeah. So if you guys need help with this, I'd be glad to help you. Let me know in the chat. I'll send you my email. But this is something that you can't really learn in 30 seconds. but it just lets you guys know the journey that Nathan and I took in order to get these Tesla coils humming.
So I'll give you a quick rundown of it, just so we can understand a little more. We're only concerned with the upper right-hand box of the primary capacitor. Mine is 0.75, so that's what I put in there. Sean's is 0.44. We skip the whole next line. We don't need that. Insert value of secondary coil. Now, this is where it gets tricky. If it's 4 inches in diameter, you divide it. That's 2. So radius 1 would be 2. Radius 2 would be 2. The height right here is the amount of your breakout line. So on the top of your Tesla coil, that little wire that's on top, that's what that is right there. That's 2. 13 gives you the height of the actual piece of PVC you're going to use. Turns is how many turns you're going to put on the coil, which is not easy to figure out. But with this, you can build this coil no problem. These are the exact numbers, by the way, of my gold coil. AWG was 32, so 32 gauge. The next line is your primary coil line. Radius, we need 1 inch, so a half inch all the way around. So that means the coil must be 1 inch bigger. So 2.5 plus 2.5 is 5. That puts us with a 4 inch diameter of a pipe. It puts us at 5 inches for our radius of our number 1 coil. The height right on the next one, I always type in 4. The next one I type in 4. Then I type in 4 again on the turns. And there's a reason for this. And then 0.25, that's the diameter of my pipe, my number 1 coil. It's a piece of copper. That's a tubing copper. That's what that is. So the reason for that is when you get down over here, it says auto tune. You click that and hit run, and it'll give you these frequency numbers based on that. And what will happen is it'll adjust the number 1 coil, like you see it here, to the correct numbers. That's the one thing Sean found out that was totally awesome. It says that our frequency of our coil was going to be 299, and that's the same thing. We're going to have to put it on the primary coil. So when we did this, okay, now that we figured it out, we have a quick understanding of it. It takes a little bit longer to learn it, but that's pretty much the understanding of what's going on. We get to the gold coil on our left right here is what it built. And then I wanted to mimic the same frequency, so we went to the same program and we did it out of 28 gauge wire. Now I wanted to show you the difference in the two. The one on the left is 32 gauge. The one on the right is 28 gauge. You want to tell them why, Sean?
Yes. So if you want to have a shorter coil, then you have to go to thinner wire. And it's all about the resonant frequency. And so if you think about it, think about those two you see here on the screen, the red and the golden color. What you're looking at is, what you're concerned with is inductance. If you have high inductance, they'll lower your frequency. And so you can get into the 300 kilohertz range as Nathan was wanting. And so Nathan was doing the conventional coil on the right. So if you Google how to build a Tesla coil, it tells you to use really long PVC pipe and thick wire. And when I first met Nathan, I said, no, we have to go to shorter, smaller, wider, thinner wire. And so Nathan, he agreed, and he got some really good results.
Yeah. By the way, I used the cheapest winder possible. I literally took the scraps from my wood pile, and I built this Tesla coil winder and wound it by hand. And you can see the results came out beautiful. But the one on the left is the gold coil. That's the one we primarily use in this, what I would tell everybody to do. The PVC is 12 inches long. The winding is a 1/4 inch off the top and bottom. So it's a pretty simple coil. It's literally a 1/2 inch less than the 12. So it's 11 1/2 inches of winding at 32 gauge on a 4 inch piece of PVC from Home Depot. So if you wanted to build that coil, that's what it is, and it's perfect for the ZVS.
I'm wondering, Nathan, if you could maybe later put in the specs in the description of your video. That way people can jot it down in their notebooks and build their own.
Absolutely. I'll
So-
put in the capacitor and everything that we used.
That's awesome. Do you mind if we answer some questions in the comments?
Go for it.
Awesome. So it says here, I was under the assumption cone-shaped and V-shaped pyramid stacked coils are inefficient. I'll be testing that with my cone-shaped and pyramid-shaped coils. So that's an interesting point there, Matt Walker. Thank you. The QUOD guy, I can't say it, says, Sean, just the grooves and the cylindrical, can't say that, shaped print. So yes, multiple cones per groove per cylinder. Okay, that's an interesting comment. Thank you. Let's see, Chris Zazula. I wish it was more intuitive on how to gauge coil sizes. Laugh out loud. You can't just weigh it. You're on to a good point, Chris. It is a little bit complicated to get started, but once you get going into it, it starts to make sense. And I'm with you. If I could just weigh everything, and then that's how it was determined, that would be a lot easier. But if you think about it, it's just wire gauge and number of turns, and that really are the big determiners when you're building your Tesla coil. So, but thanks for sharing. That's a good point. Let's see here. Chris says, then you gotta wonder solid conductor versus stranded versus planar. So Nathan, what do you think about that question about solid conductor versus stranded?
On what part?
Yeah, that's a good
Oh,
question.
you mean the number one coil?
That's what I'm guessing.
I prefer the solid here. It really doesn't matter. It matters the capacitance of what you have. So it's like Sean on his LCR meter, when he puts the thing on it, he sees exactly how much capacitance it has, and then he adjusts his capacitors to it. So it's not necessarily a bad thing. Like, for instance, I have a stranded wire that I use for another coil, and it goes to my not ZVS, but my Slayer exciter, and it works just the same. I also have solid wire, works just the same.
Yeah.
The individual wires will dissipate heat a little better than the solid wire will. Once the solid wire heats up, it takes longer to dissipate the heat. But the advantage to something like this right here is, in future experiments, I'll show this, and I'll credit Sean and Charlie C for this. When you put a water pump on the number one coil, the advantage is to heat the water itself so you can get more amps into your coil. So there's a trick there, and Gerald was showing me when he did his water coil what it was. We're going to be able to change some of the stuff in this coil later on, but I'll just keep it basic for now. I prefer the copper tubing for this type of coil for a basic original setup.
Yeah, thank you for that, Nathan. You make some good points. The copper pipe, you can definitely run some water through there to cool it down, and then run some serious amps. Also, too, when you're up into the higher frequencies, electricity tends to run on the outside of the wire instead of the inside of the wire. So if we're running copper tubing, then we're not wasting any wire because the electricity just runs on the outside. Also, too, it's a lot easier to deal with shaping the copper tubing. Well, I don't want to say easy. Once you start shaping copper tubing, it keeps its form. So you don't, if you had other types of wire, it always loses its form. So that's another positive for doing it this way. This is 1/4 inch piping. I've moved to 1/8 inch piping. It's easier to work with. It has the same positives, and it's a lot cheaper. So just a tip there if you guys are interested. And we're also seeing some more questions in the chat, Nathan.
Okay, well, we'll get to a few more questions here in a minute. I want to kind of get a little further into the presentation, if you don't mind.
Awesome. Let's do it. Thank you. Sounds good.
Let's just show you the winding on that coil, by the way. You'll never believe a lathe didn't do that. That was all by hand. And I'll leave a link to the how to wind this thing and how to make a real cheap winder for it in the description, but you could see it came out beautiful. So here we go. We're finally set up the right way. I had to change the switch to the negative, positive, and I can tell you Sean's drill sergeant personality comes out when you do this stuff. He sounds all nice, but wait until you start messing up. Very clear, very direct, and do this. I didn't say to do this. I said to do this. Send me the picture. Okay. So no, I'm just giving Sean a little razz in there, but no, he helped me out with this and getting it set up and getting the right capacitance in it. We worked that out. We worked out the switch. He wanted to see on this the power source here, if it actually was dropping or fluttering on the power level when you turned it on. You want to go ahead and tell him why, Sean?
Yeah, so the ZVS circuit's it's a bit finicky. It doesn't just want to oscillate on its own. And the power supply, normally the DC power supplies you buy, like the one there on the left, again, they have this sort of smooth increase in power as it works, but the ZVS prefers a jolt, and so that switch there added between the power supply and the ZVS allows you to give it that jolt that it needs to start oscillating. And one thing you'll notice when it's not if it's not oscillating, you'll have high current and low voltage on your power supply. If it's oscillating, you'll have the high voltage, the voltage you put in, and then you'll have very low current. And that's a key tip on knowing whether or not it's oscillating.
And one of the things I'll say on this is when you blow them offset, the quickest way to see it is on your power supply here. Because if you put in 20 volts, it'll go down to 15 or 14 volts right away. And you'll see that it's out of oscillation, and it means that you probably have a burnt up MOSFET.
That's a good point, Nathan. Let's say you put in 20 volts, you always want to watch it, make sure it's 20 volts. If it drops, it's a burn MOSFET, or if you just turned it on, it's not oscillating. So you always want to look for that voltage, like Nathan just said.
And it'll be key. The one on the left-hand side that goes, and by the way, the wires are set. The right-hand side always goes to the bottom of the coil. The left-hand side goes for the adjustment. Always on this, exactly the way you see it. And what will happen is the side that goes to the bottom of the coil, that's the one that the one that's opposite of that. So the one that goes with the little clip, that's the one that blows up on you. That's every time, that's the culprit. The other one stays cool. And it goes that way only because that's the side that's going to get the most heat. As you turn on the system, if you're out of resonance, that clip will heat up. But when that clip heats up, so does that MOSFET.
That's another good point, Nathan. The alligator clips start to smoke if your MOSFET's blown. And I've seen that before. It's worth noting, too, if you look at the clip there on that copper tubing, it's at a specific location to get a specific inductance that works at the resonant frequency of coil 2. And so it's a little bit of labor of love to find that sweet spot on that coil with your alligator clip. And so later we'll come up with a better method. But right now, Nathan's tuning it here by moving that little alligator clip up and down the copper wire to find that sweet spot.
So just so you guys know, when you're tuning this, it's very important to understand where the drop-offs are. And here's what I mean. You're going to get to a frequency in this. So if you set it right around 300 kilohertz and you've tested your number 2 coil and you know it's there, When you're putting the clip on, you're looking for that range. You want to be, 300, 340, somewhere in there, and then move the clip along, and you'll see it on your oscilloscope as it goes down. So you're going to try to get it right around that 300 mark. You know when you hit resonance because radio frequency resonance drops off a cliff. And what I mean by that is you'll go 320, 320, and then it'll go like 420. And you're like, whoa, hold on a minute. What just happened there? Well, that's the point where you just dropped it right out of resonance. So back up just a little bit and turn it on again, and that should be your perfect resonance point right there. It's the fastest way to find it. If you try to dial it in by the point something on your oscilloscope, it'll take all day. Simply move it around till you can find the drop off where you're on the same winding line right there. And then all of a sudden it changes the frequency by a lot. And that's your drop off point. Move it just a hair back and you're resonating perfectly.
Good points, Nathan. Thanks for sharing that. And one more thing, if you don't mind to point out,
Go ahead.
is that everything's copper. We're using copper for everything. The reason for that is if you were to, let's say, use steel or iron or some other metal, is that it would heat up. It would have resistance in your circuits, and it would give unwanted heat, and you'd lose power. It would hold a lot of the power and turn it into heat if it was steel. And so that's why we use copper for everything.
So this is the radio frequency method, and I'll show you the connections in a minute. But all I'm doing is I'm checking the frequency, and you see how it gets real big right there? And then I stop, and it'll say, 310, 320 when we're about finished. So right there, it's in resonance. Now watch, if you turn it down just a little bit, it goes away. You turn it up a little higher, it goes away again. That's what I mean. There's your drop-off point right there. It'll immediately be in resonance and immediately fall off. So one of the very quick notes about this, once you know you can find it in your number 2 coil right there, because that's all I'm testing, then you need to make sure that goes to your number 1 coil when you get the frequency. That's what's going to make tuning it a lot faster. Now, God, I forgot what I was going to say. With that said, let's move on to the next one, and I'll show you this right here. 318 kilohertz is what we came out at as the perfect resonance frequency. When we did Java TC, Java Tesla Coil, we wanted 300 kilohertz. We were off by 18 kilohertz. That's about as much as it was off, and it pretty much shows up the same way. I can probably say that might be human error on my part. I might have added a half-inch more of winding to it than I should have. So 18 kilohertz, not too bad. Still within our range of our ZVS, so I figured it worked perfect.
Oh, and Nathan, you're spot on. It's when you're in the ballpark like this, you're going to get good resonance. A lot of factors that need to be considered: temperature, moisture in the air, and so it will cause the frequency to vary. So to be within this range is really good. Oh, also there's imperfections in the copper wire, so nothing's perfect. But Nathan really nails it here, as you're going to see in the output.
Okay, sorry, give me 1 second.
No worries.
Oh, all right. Now, I got to tell you this. Sean showed me this, okay? And this confused the living daylights out of me. He's going to run AC on this, and he'll explain it. But this is what he gives me. He goes, Nathan, just make one of these, and we're going to run some AC and some high power through your Variac. And I go, oh, the last time I ran my Variac, my whole thing started smoking, Sean. And he goes, don't worry about it. We got it, right? So I'm going to move ahead just a little bit, Sean, to right here, and I'll let Sean explain why.
Sure. Thank you, Nathan. So the ZVS power supply needs a positive voltage and a negative voltage. So that's why you'll connect the red to the positive and the black to the negative. But if we want to run AC, then we're going to need to put a diode somewhere in between the connection of the variac or the AC to the ZVS. So placing the two diodes here, and it doesn't matter, one diode will work. These are just two diodes, so it can handle more current. But by placing the diodes in this configuration, you're cutting out the negative part of the sine wave. And in cutting out the negative part of the sine wave, all you have is the positive part, that positive hump. And when that positive hump slams into the ZVS circuit, it gives you those wild arcs, the swords that come out. And so that's basically the principle behind this.
Yeah. So when Sean showed me this, by the way, I quickly pointed out, hey, Sean, did you realize that these diodes are backwards?
Yeah, that's how it works.
So, yeah, this is a whole lesson in there. By the way, just look at this for a second. So let me see if I can't zoom in on it a little bit. He is telling you right here, okay? Connect to the positive terminal. And if anybody knows anything about electrical, you go, well, the white's coming out, that's neutral. The black is hot. The green is ground, right? So the ground's tied off, it's not used. You go, okay, we can understand that, right? The neutral is now going to your positive, and you go, oh, that's a head scratcher. That must be backwards, right? No, it's not. It's right. Then the hot is what gets the diodes, and you're thinking even worse, they're backwards. So, and he's fully confident that this thing's going to work, right? Because he's already done it. And let me just tell you, when I first looked at this, I go, there's no way. There's just no way. This guy, he's going to make this thing blow up on me.
Right?
Yeah, I thought he messing with me. You know, hey, let's just blow some of Nathan's stuff up and we'll see how it works, right?
Well, Nathan, if you zoom in on the graph paper on the right, this is what I was sending Nathan. I didn't know him, and I'm going, do this, do this. So it was good fun. It was good fun.
That is, I have to say, that is a nifty little device there.
Yeah, it's totally deceiving. You would never think to do it that way. Not unless you're Sean.
Oh, you're too kind. Look at that, man.
So that's our first run. We were doing a live show.
Oh, that was during a live show?
Okay, so we're getting ready to do a Tesla Coil live show, right? With Ben and I. And I didn't have anything going. I couldn't get this thing to work, right? And I was just having all kinds of trouble because I didn't understand that little clip that was going on there for my primary. And 5 minutes to go, I had a masterful idea. Okay. I said, all right, this thing's not working. I'm going to get it the best I possibly can, cross my fingers, and shoot for the moon, right? If it blows up, at least I had something to show. So I get this thing and I find the drop-off point. I move it a little bit back and I go, oh, God, let it work. Okay. So I ripped voltage to this thing. And right here, I just get a little bit going. I think I'm at like 30 volts. Okay. We get to the live show and I rip 60 volts through this thing at just massive current. So I want to, and this is what I got out of it. We got a 11-inch.
Remember this video? Yeah, this was crazy.
That's huge. That's, I mean, if you Google 11 inches, it's close to 1 million volts. I mean, of course, it's very low amps, but the voltage on this is insane.
Yeah, so with Sean's guidance, man, right before showtime, we got it going. We were able to show on the live show it working perfectly.
And also notice that the windings are on the exterior of the PVC pipe, and it's only one layer, not multiple layered, like I'll be showing you in a little bit. And so there's a unique shape of the plasma with that coil 2 configuration. The long pointy swords that come out is that. And so one of the comments, it talks about how geometry matters. And that is very true in building these. Different geometry Tesla coils give different geometry plasma. And so we'll be showing that later. But good point in the comments.
Okay, so this right here is the radio frequency method. So here's what you do. You take your probe and you're going to hook it right to the side of the number 2 coil. And then you're going to put a 20 K ohm resistor right there. And that connects on the other side of it to the positive of your frequency generator. On the right, both your negatives connect in from your probe and your frequency generator, and that goes to earth ground. And then you scroll through the frequencies and you see which one goes the highest. That's pretty much the way that I did it in order to figure out exactly the frequency of my number 2 coil.
Yeah, that's a good point, Nathan. There's 3 values that are important in building a Tesla coil, just 3. One of them is the resonant frequency of this coil here that Nathan's measuring. The second is the inductance of coil 1. If you have the inductance of coil 1 and you have the resonant frequency here of coil 2, then it'll tell you what capacitor to use. And so that's basically the Tesla coil. If you know those 3 values, you can master the Tesla coil.
So here's a quick video. You're just going to see my red Tesla coil, and we have it in DC mode. We're not in AC, so no big sparks. We're just going to check and see how far the light bulb goes out. So far, we have 12 volts. And we're lighting up right around 2 feet. Now we're at 25 volts. And we're closer to 5 feet. With very little breakout. So as you can see, we have a really efficient coil right there. And its resonance frequency was 340 kilohertz. So I was off on this one by a little bit more than I was the last one, but I also added 1 inch longer of windings on this one. Just so we can be sure, because it was 28 gauge instead of 32 gauge. So I figured I'd be off by more. I should have stuck to the original plan on this one. And that's all I have on that part of it. Give me 1 second. So we built both of these coils. Let me just tell you, in the description of this video, when we're done, I'm going to go ahead and write the exact stuff that you're going to need. And I'll just tell it to you now. Buy 32 gauge wire. Do not just buy a little roll. Buy at least, a pound on the winding. You're going to probably want it for other projects. It's about $32 on Amazon. Go to Home Depot, buy a 4-inch wide pipe. And just try to make it as straight as you can when you buy it. Usually helps, because you're going to want to make more Tesla coils after this. You're going to cut it at 12 inches. You're going to wind 11.5 inches of that. So you're going to leave a 1/2 inch off the top and a 1/2 inch off the bottom. Go ahead and mark it and wind it. Now, you're going to use some clear coating on that. I use urethane. It comes in a black can. I'll go ahead and write the name on it when I put it in the description. But I spray it. Once the thing is wound, I'll leave it right there on the winding stand. I'll bring the winding stand outside. I'll spray it. Just a real light dusting coat. You're not looking to make this whole thing really filled with lacquer right now. You're just trying to get it a little bit. That'll tack it up. Come back 10 minutes later, tack it up again. Do not try to overdo this thing. You're going to build this thing 3 layers a day. The second day, you're going to do the layering again. Then it should be perfect. Now, I'll leave the STL files in there for a 3D printer so that you can print off the bottom of this thing and also the cap, so that you have everything that you're going to need for this coil. Then on the number 1 windings, you want to wind 8 windings of 1/4 inch copper to me. You can get it at the Home Depot while you're there. Sean used different windings. If you want to use those, you're welcome to do so. You can get them on Amazon. But just for this sake, we're just going to say the 1/4-inch copper tubing at the Home Depot will work. Now you're set to go. All you have to do is take about a 4-inch or 5-inch piece of copper, solid copper from like wall wire or anything else, and you're going to make a breakout. At the very top, you're just going to simply cut it like this at an angle. And what that's going to do is give you a sharp point for the breakout. That's exactly what you want. You can solder the number 1 winding directly to that on the very bottom part of it. And it actually has a groove in it in the STL files that you're going to get. And that'll allow you to sit it in that little groove, put some glue on it, and you're good to go. Also on the very bottom, there's a hole underneath, and it tracks underneath the flat part, the little hole. So you could put the wire in there, soldered on, and then move the wire out so it never sits funny when you have it in there. Everything is perfect for this. If you build it the exact way we built it, you get 2 capacitors from the Amazon, 1.50 nanofarads each. They're high voltage capacitors, high frequency. Do not try to just get high voltage. It has to be high frequency. They are for a Tesla coil. And I'll put the link for those in there as well. You get those. Get your little switch for your negative. And all you got to do is get a power source. Now, on this power source, probably 40 volts is all you want to go on DC. On AC, that's a whole different story, and we'll leave the picture in there so you guys can look at it and buy the diodes. On there, Sean put the actual diode that you would need for this project on there, and then you'll connect it exactly the way he said it with the Variac, and you'll be able to set this thing up. One quick note on the whole thing: if you do the Variac and the AC, if you hear any humming in your Variac, stop immediately. Do not go any further. Find out what you have wrong. If there's humming, you'll get back feed in it. And I'll let Sean describe that now.
Yeah, good point and great explanation. You've really sort of codified or simplified the Tesla coil that we worked on. If you guys really keep to the PVC pipe measurements, the 32 gauge wire, the amount of windings that Nathan mentions, the copper tubing, the 1/4-inch copper tubing, you're really going to have a working Tesla coil. This Tesla coil will always work for you. It's not this sort of vague, oh, maybe it'll work, maybe it won't. No, this is a tried and true. Nathan's beat the heck out of it and it still runs. So, if Nathan has it and still runs, that it's tough. It can take a whipping. And also, it doesn't matter if it's 1/8-inch copper tubing, 0.2-inch copper tubing, or 1/4-inch. The windings are going to be the same. If you have 9 windings of 1/4-inch, you can do 9 windings of 1/8-inch. You're going to have an advantage with the 1/4-inch, of course. You're going to have more space for the electricity, so it's going to have less resistance. But I just picked the 1/8-inch tubing because it's cheap. So, yeah, Nathan, great job, great explanation. Ben, you want to say something or say more?
I just want to say I agree with you that Nathan has found a way to break down the mechanics behind a Tesla coil for layman's like myself to understand. I thought I would never understand how it would work, and I'm finally starting to piece it together. Not entirely, but thanks to you guys, I appreciate it, and your presentation has been helping a lot. Nathan and his explanations also.
I appreciate that. Yeah, Nathan's got the lead on this one. Doing great.
So I'm going to show you one more video, and I just want to show you when a thing goes bad, and then we'll let Ben take everything over. So,
okay.
Oh, hey, in the chat, we'll look at your questions after as well.
Okay, so here I am running my Tesla coil, and I'll just let it play. Here we are, we're at 40.
$40 volts?
55. By the way, you can start to see it smoking right there on that little clip over there.
Love it.
Let me just tell you, you're not going to deter me with a little smoke.
It's awesome.
Oh, okay. Well, I need to get a much bigger wire, apparently. This is not working this way. All right, here we go with test number 4. Well, I'm on test number 4. It's absolutely hilarious because I know it's out of resonance, right? I completely understand it's out of resonance, but I'm trying anyway. But
And just a quick tip on the Variac, it's pushing back against you because you're pumping some serious current.
oh yeah,
The
So-
Variac should always be smooth, not hard to turn.
oh that thing was humming. Yeah, it was hard to turn. So I think I tried it about 6 times that day, and I kept frying it. So I think it's absolutely hilarious now that I look back on it. I really didn't know anything. And here's a good picture. Here we go. Nathan and his frying to find out, right? There it is. It's just on fire. You see all the smoke. So, yeah, that's when you know you're in trouble. Okay. With that said, I'm going to show you something right now. This wire, this little cheap dollar store wire, okay, we've all got them. They don't run very much through it. This is what I can use instead of that clip right now on any one of my Tesla coils, and it will not burn up. This little cheap dollar store wire. So when you see people go, oh, you need a battery cable or you need a number 10 wire or something like that, you don't. Once it's in resonance, the amps go through it so fast that it will not even burn this little tiny wire. That's how you know you're in perfect resonance. You won't be burning things up. You won't be like me. It'll just work. And I'll say this. You got to remember this thing's a transformer. So you're going to take your amps and you're going to convert to volts. But it doesn't convert 1 to 1. So it takes all the amps that you're pushing into this thing and it converts them to voltage. And the voltage itself builds up to such a high level that it shoots out the top. Remember, your number 1 and number 2 coil are not connected. So transferring amps is a little harder than you think. So it'll come out as voltage out of your number 2 coil all the time. Remember, it's a resonance transformer air core. There's no core in the center. It's just hollow. That's why they call it the air core. But it's a resonance transformer, so it's going to convert from amps to volts, and you're going to get a lot of voltage, very few amps in your number 2 coil. If you had all the amps that you think you're pumping into it in that number 2 coil, it'd be on fire. And it's just not. So you know it's converting.
Yeah,
So,
it's a good point, Nathan. A well-balanced system and perfect or near perfect resonance, you'll find that you'll get lots of plasma, but you'll be putting in the least power. And that's why it runs on that little alligator clip when it's tuned. So it's all about tuning. And you only need to heavy, thick wires if you want to run Tesla coils that are not tuned.
yeah. Okay, that's my presentation. Thank you, Sean. Thank you for helping me out on that. I really appreciate it. And guys, I will absolutely leave the information for you in the description of this video when we're done.
Awesome, Nathan. Then Ben has some big news to share, and then I'll have a small presentation after. That sounds good.
Sounds great. Ben, what do you got?
So I got a 2-parter. It's not going to take more than maybe 15, 20 minutes. But the first part is all science, a couple of breakthroughs, and then the second part is infomercial. So for the first part, we have a couple of breakthroughs that I've had recently. I've been waiting a long time to test the efficiency of the magnetic rotary for our system specifically. Now, we're not actually testing the rotary in this video. We're simulating it. So what I mean by that is we're spinning a neodymium sphere in the center of the vortex and seeing how efficient or how it affects the efficiency of the system. And I have a wattman on the wall going from the wall directly to the power supply, workbench power supply, which is going to the stereo amp mini board, then to the coil, and then to the load. So here's the first video and the results of that, which are really amazing. All right, Wattman.
All right, everybody, here's something really cool. We have the stereo method hooked up right now. Okay, 10 volts from our power supply at 140 milliamps. Okay, we're gonna spin this little neodymium magnet and we're gonna monitor the wattage. Okay. Oh, it's not gonna show it. Oh, you gotta show it. There we go. Okay. So, 7.3 because we don't have it on. We're gonna turn it up. Check this out. Okay, let me take that. I'm gonna take the magnet out first. Okay, we're gonna turn it on. I'm turning it up. Look at the watt consumption. 24 watts. Okay. Now watch this. We're going to put the neodymium magnet in there, spin it up, increase the frequency. Now check this out.
That's not even as fast as it can go, by the way.
Wow.
That's so cool. Awesome.
That blew my mind.
And
That's
it goes
amazing,
back up.
Ben.
24.
Amazing.
We saved 10 watts of power by spinning this thing.
What?
Oh, yes, 10 watts. Indefinitely, that's measurable. And the cool thing is, when you calculate that, that's a 41% efficiency gain. That's
Wow.
incredible. But we haven't been able to apply that specifically to anything. There are ideas that I have, and I'm going to go into that in later date, not tonight. But yeah, that's very big. I was
Huge.
amazed. Yeah, because in Daniel Nunez's videos, you see him get like maybe a watt reduction, and it fluctuates between 4 or 5, and he originally had 5. This is a significant reduction with the neodymium sphere spinning. Now, granted, we have to we have to account for the weight of a rotary that's going to not maybe spin as fast as the neodymium sphere. But if we can incorporate that sphere spinning with the perfect design for something like this in any way, that would be ideal, because you can get that. That's not even a fraction of how fast it can go. I've gotten to go way faster. Like, it scared me how fast it was going.
So that's completely awesome, Ben. I just want to throw something out. You were talking about putting a rotary. I would recommend you look into what is called a magnetic bearing. If you look up a magnetic
yes,
bearing,
I did. I heard about that the other day. You're right. I did write that down in my notebook, because that did strike me as something that would be a potential candidate.
Yeah, it has no friction, so
Right.
it won't be too much of a drag as you spin up the rotary if it's magnetic.
Nice. Yes. So I like that. I like that suggestion, because that's something that I think is an alleyway for us to go down this road.
That's tremendous. This is a huge, amazing discovery. In the comments, people are saying extremely awesome. That is amazing. Nice. Lots of love in the comments. Great job. Great job, Ben.
It's a big day. And this is only half of the breakthrough, guys. This is only half of it. So I have another video for you. This is big. This has been a big day, a big week, a big month.
Huge.
This ride has been a real roller coaster, but we finally are at the apex here.
That's amazing.
And yes, a lot of great news. So I'm gonna take that down and bring up the second video.
I'm sorry, Ben. What kind of load are you looking to put on the output?
So I'm glad you asked that, because with the system, we found that we have to have a load that's in resonance with the system, right? We can't just put any load onto it, you know? And not only that, in this next video, you'll discover that it's not just the load that you have to consider. I wasn't considering the source, the battery. So, right. But specifically the devices that I am using, we're just looking at efficient like heating and lighting for off the grid applications for, say, your power goes out in the winter, which is what I'm afraid of. And I have a system now, finally, that we can actually have some kind of lighting and heating. And I know exactly how to do the heating. I haven't released that information yet, but it's very simple. And nice. I will in the future, the near future. Everything I do is open source, by the way. I don't really keep, there's a couple of proprietary things that I have, but most of it, like 99% of it is open source. So
yeah, you get comments, Ben, about them wanting to see it again. Do you want to
see it again?
Or just run it real quick?
I have one question for you, When you do your load on there, Ben, have you ever thought of taking two batteries and connecting them together to make sure they're equal 100%, and then put one as your source and one as your load?
No, but that is a good idea. I will get with you after the show so you can like walk me through that process, and I'll write it down and then test that. Because definitely that's something that I'd want to test. We ideally, I don't have two 12-volt batteries right now. I have one 12-volt. But when we have two 12 volts, that's ideally what we want. We want, because we want to test the Bedini stuff, obviously. So that's definitely going to be on the candidate list for testing.
Yeah, because it equalizes your voltage and amps in both batteries, and then you know what I mean?
Yeah, that's a very good thing, a very important thing to consider. Thank you.
Okay, let's see the video again.
Yeah, awesome. See. Oh.
So good, we want seconds.
So I had to turn off the power supply.
All right,
and turn
everybody,
it back on.
Here's something really cool. We have the stereo method hooked up right now.
The power supply doesn't really handle this very well, and that's what I found out recently.
Okay. 10 volts from our power supply at 140 milliamps. Okay. We're going to spin this little neodymium magnet, and we're going to monitor the wattage, okay? Oh, it's not going to show it. Oh, you got to show it. There we go. Okay.
Next video, I'll try to get a clip of the power supply number 2.
Because we don't
That's
have
something
it
I
on.
didn't include.
We're going to turn it up. Check this out. Okay, let me take that. I'm going to take the magnet
We did see
out
in these
first.
videos the current going down.
Turn it on. I'm turning it up. Look at the watt consumption. 24 watts. Okay. Now watch this. We're going to put the neodymium magnet in there, spin it up, increase the frequency.
Start around 7 hertz. Ideally 7.83 to saturate it in that natural Schumann resonance, but 7 does the trick.
Now check this out. Wow.
Awesome.
And then it goes
Nice.
back up. 24.
Wow.
We saved 10 watts of power by spinning this thing.
Crazy. So awesome.
Yeah. And that's just the tip of the iceberg. Check this out. Watch this. So this is split up into 2 parts, mainly because I got a wire disconnected and I had to stop the video. That's all.
All right, you guys are seeing this here for the first time today. We have the multimeter hooked up to the 12 volt, 20 amp hour battery, which is what Bedini recommends for these kinds of systems. As you can see, it's at 12.82 volts without anything connected, okay? Once we connect it to the Lightning Thief, notice the voltage drop, and not only are we able to power both of the fans at full RPM, which is 12 volts minimum to do that for both of them, we are also able to light 3 of these neons. No, 4. Yeah, 4 of them. So check this out. This has not been witnessed before, and monitoring the current on the output and the input gives us the exact same current.
So real quick here, before in my previous videos of the modified Jewel Thief that we've been working with, which is all on my channel if you want to know how it's built and everything. Everything, like I said, everything's open source. Before we were able to light a single neon lamp or a couple of them, but we weren't able to then connect a load like 2 fans or a LED panel, for instance, and have any kind of useful work, right? The fans would barely spin when they were connected, and it just wasn't translating the energy very well. And I discovered that the battery, the source, has a lot to do with that because it's not in resonance.
So check this out. This is really, really significant here. Okay.
By the way, every time I turn on the light on that multimeter, the voltage spikes a little bit. I don't know why, but all right, this is where the wire gets disconnected and I stop the video. Let me play the second part.
Sorry about that. The wire got disconnected. So check this out. Watch this crap. Look at that.
I was not expecting this.
Look at that. 4 neons, and this is full speed.
Wow, those are cooking.
Checked out, but not only that, check out the voltage. Watch
When
it
it stabilizes.
Oh.
Voltage actually starts
This is going so
dropping.
freaking fast. I gotta keep
Slowly,
an eye on
not
it.
crazy.
Look at that voltage drop. Watch it drop.
What was its original? Was it 13 volts?
No, the 13, it spikes when I turn the light on. It's originally 12.82 or 12.83.
Okay.
See it drop? It'll keep going down. Now
Seen
watch
it go
this.
into
Let's take a look at the
0.58.
current. Okay?
Just happened today, by the way.
16 to 18 amps, milliamps going in. All right? About 17 milliamps to 18 milliamps going in. All right? Look at what's coming out. The exact same amount. Okay? One more time, right in the input of the coil.
WTF.
This is before it's hitting any of the circuitry or the coil. 17 milliamps going into the coil, 18 milliamps.
So
I
that's
wasn't
the
expecting
unity.
this. The fan never goes that fast, so it's not set up. I had to tape it down.
That's unity, man. 100% in and out.
Look at that.
That sounds like an
There's
airplane.
even more on the negative.
The negative, correct.
This is insane. This is absolutely crazy. The lightning thief works. She
Wow.
works.
Nice.
Holy crap.
You're a little bit excited. It's awesome.
I'm still
And
ecstatic.
watch it go back up. Climbing back up.
It's so cool.
She's all the way up.
Wow.
So freaking cool.
So just to get it straight in my head, so you put an input voltage of 12 volts, roughly 17 milliamps, and then you read the output after the load, and you're getting 12 volts, 17 milliamps.
No, see, that's the thing. Those neons, to light 4 of those, at least
Yeah.
300 volts. At least.
So, holy cow, you're
Yes.
powering up some heavy duty stuff.
I was not
Wow,
expecting
keeping-
that, Sean. I was
Yeah.
absolutely, I was like, maybe one of them will light up when I get the fan and it'll be chugging along a little bit. It took off. It absolutely took off. The Lightning Thief is a complete success. We're going to be testing how long this is actually going to last on the 12 volt, and then, do another comparison how long it lasts without the coil. Obviously, that's going to be the next test that I do, and I'm going to do that all live. But the most exciting news is I had a lot of people recently reach out to me asking me if I'm going to start selling these devices that I'm working on. And I can't sell the coil but I am going to start selling kits, and I'm going to be starting to. I'm going to start by giving out to our team members who are working on the coils a Lightning Thief Mark 1.
Nice.
So,
Wow.
yes. So everybody who wants one on the team will get one. I'll ship it out to you free of charge. You know how it works, but I want you to have something nice that you can. Obviously, I'm going to replace this with a screw terminal, but yeah, I just want you to have something nice that works.
Ben, let's put you up on the solo. Let's take a look at that box that you built for it on your 3D printer.
Oh, wow. You designed that box?
Yes, it's got my logo on it, the star, the sacred gem, the 2 pyramids. It's kind of hard to see, but the neon light lamp indicator is in the middle, which is really cool. Yeah, it'll just FYI, it has to be tuned. You have to know the tuning of your coil, and then you open it up and replace the potentiometer. So we are going to be, or I am going to be selling these. And specifically, I think I'm going to be selling them with a potentiometer. And then what you would do is find the resonant range and then replace that with a resistor. And it's very simple to do. I just wanted to I just wanted to streamline the whole process. But I have one more quick thing.
It's Christmas.
Yes, it's Christmas. So a happy Thanksgiving, everybody. So this is our new lineup. I hope you can see that. Trying to streamline this process for the team and anybody who is interested in buying something like this to help support my research into the coil. So right here, it's going to be green. It's not green right now, but this is the green machine. It's going to be used as our pulse circuit. It's an all-in-one system. It'll be like replicating the stereo amp setup that I have used to pulse a magnetic rotary. And you can see, I'm not going to be selling this one. That's just what I'm testing with at the moment. But a magnetic rotary will be sold as well.
What's the price of your lightning circuit, if you don't mind me asking? Do you have an estimate?
I do not at the moment, but I will guarantee that it will be very, very cheap because I want this this technology into the hands that need it the most. Obviously, that's my main goal, and if I can, do that, that will be very essential for people who need stuff like this.
It's amazing. I can't wait to
or need
play
to test
with it.
Yeah, or want to test with it, and improve on the design or something. That's what I'm hoping that you guys will do. Use it for your own research. Use it to help you streamline some of these processes. But I am going to be doing a test tonight. Not on this podcast. I'll start another stream. That we'll be testing how long this thing will last on the 12-volt battery tonight.
Nice.
You're getting people in the chat saying we will buy it from you. So you got some good interest.
Yes. So if you're interested, please email me so I have like an idea of how many of these to actually manufacture when we start rolling them out. So we have enough. I don't want to get to the point where we have a rollout and it's like like 100 people want them and I only have like 5.
And you say this is open source. Do you mean the diagram of the schematic that you're going to draw up?
Everything that's in this box is open source. The circuit is using Michael's modified Jewel Thief circuit. It's basically a modified version of Daniel Nunez's ABHA excitation circuit. So we already have a PCB being printed out that Michael was gracious enough to go through the process and make. There's a manufacturer who's sending us a few to test with. To see, what we can do with the case that we have. I kind of like how the indicator and the logo is, but it might change. And obviously we're going to replace this with a proper input, a screw terminal or something. And also it's not official if it doesn't have the benefactor's seal of disapproval. So
that's awesome.
Nice.
Hey, Ben, can you throw your email in the chat? People are asking for it.
Oh, yes.
Yeah, and then also your channel. And your channel has your email linked to it, right?
Yeah, it's got my email, my Patreon, if you want to keep up to date with some of the stuff. But it all comes out on YouTube eventually. I just, use the Patreon as a fundraising mechanism. So this is my email.
There we go. There's Ben's email right there.
Awesome.
And my channel. So yeah, anybody who's interested in purchasing something like this, let me know in the email, and let me know, give me a fair price point, what you were willing to pay for something like this, so I have an idea what's fair. I don't want to overcharge. I want to keep it as costly as possible, because it's very simple. Very simple.
Awesome, Ben. Thank you for sharing.
Of
No,
course.
that's an awesome update, Ben. You did really good, man. I'm really proud of you, man. You did good.
Thank
Awesome,
you.
my man.
That means a lot to
Awesome.
hear you. Yeah, it means a lot to hear you guys say that. It really does.
You deserve it, man. You got this one. You reverse engineered it. You took the time to look at everything, and
Yeah.
hey, big time, man.
Yeah, big hand of applause.
Thank you.
I've worked with engineers before, and you're a natural, Ben. Totally.
Thank you. That means a lot.
All right, Nathan, do you want to do a bio break for 5 minutes and then jump into my presentation, or do you want to postpone mine till next time?
It's really your call.
I'd love to do it. I would love
let's
to share
get
my
it.
jump.
If you're ready, man, let's go.
Do you want to do a 5-minute bio break, or you just want to go?
I'm good. Are you?
I'm good.
Then
Ben?
let's roll.
Yeah, I'm good.
All right. Let me see if I remember how to do this. Let's see. It's doing that thing again.
Oh, give me a second. We got a lot of stuff on here, so I'm looking for.
Okay.
I got it. Okay.
All right. So I can expand it now?
Yeah.
Okay. How does it look, Nathan?
Perfect. You're good to go.
Awesome. Well, hey guys, thanks for hanging on this long. I'm just going to go through some of the things I'm working on. So what you're seeing here on the screen is what basically is the secret to all my coils. I have these grooves that are 1 millimeter wide and 1.5 centimeters deep. For the spheres, I do one centimeter deep instead of the 1.5. But this is the secret sauce. You just wind the copper wire in between these grooves. Right now, this coil here is 2 inches, 2.5 inches. And in each groove, I can wind over 225 turns of wire before I go to the next wire. So when I'm complete here with this small coil, I get thousands of turns of wire. Here's sort of the methods that I'll use. I'll grab the drill. I can't go too fast because there's a gap, and that gap allows me to change rows, change grooves, so I can wind the whole coil. But I kind of want to just give you a little peeks in how I build things, how I work on my coils.
That's very crafty. I was wondering how you would do something like that. This is how I would do it if I'm going to build a coil like this. It's perfect.
Oh, thank you. That's a record turntable in the back from an old record player, and this is my drill. So it makes things easier, definitely.
Yeah, that's brilliant.
Thank you, Ben. This is me unwinding a coil because I made a mistake. So I'm very picky. I don't like to solder or resolder. So I'll go through the hassle of hand unwinding. And this is another method I use to unwind my mistakes. Now, it's not always like this, but I made some decisions on this coil and changed them. So that's why I'm unwinding them. But here again, it just shows you how it just slips real nice, and it'll unwind. If you have bigger coils, I won't use a drill, but the coil on the turntable is always one of my tricks, if you will. I got that at the thrift store, so I'm a big thrift store guy. So here we go. We're looking at, oh boy, do the math. I think it's 11,000 between 11 and 12,000 turns of wire. And it was only a couple days and only an hour or two per day. So it wasn't too bad. I find it relaxing to wind coils while I'm watching YouTube videos. So it's very therapeutic. It's, you know, some people knit, some people crochet. I like to coil. So here you can see it in scale, Sharpie. This is the regular size Sharpie. I have a lot of spheres that I'm winding. So the big one on the left here is PTFG. So the PT materials. This middle white, these two smaller ones, that's pure nylon. And then to the right, the black ones here are PLA, which is the normal filament for printers. So I'm putting the black coil into a form here in green. And I just grab junk out of my bin and hot glue it. And I'm trying to suspend the coil so the coil doesn't sink all the way to the bottom. So that way the resin, the epoxy, can cover the top and the bottom. Here's another look at it. Soldering the wire to a thicker wire is key. Here's one of my methods that I use around the outside here because I'm putting a drill hole in the middle of the epoxy. So this method, so it looks great and it always works or almost always works. Here's an idea of what it looks at the bottom. I know people like Ian are trying to build these, so I'm giving extra details on how I do things. So before I pour the epoxy, I will seal it because I have to have the negative wire come out as well as the positive. Here's what it looks like out of the epoxy. And there's a big lighter to show you how small this thing is. I nicknamed my coils. So this coil I call short stack. It kind of made sense and sounded good in my head, but it's a terrible when you try to say it, but it is what it is, short stack. There's another close-up of it. I just love the way the epoxy and the wire sort of make sort of an amplification. Very pretty. There's how big the coil is, fits in the palm of my hand. The copper tubing I'm using is 1/8. So here's I'm showing that it's working quite well for my purposes. And you get a whole lot more of this for cheap since copper is not cheap. Another picture of it in my hand. This is the circuit that I'll be using. So it's a ZVS circuit. In the past, I've used 2 circuits from the YouTuber schematics. Here I'm using the ZVS board from SciTube and Archangel. You can go to their YouTube channel. They offer free downloads of their Gerber files. If you take the Gerber file and upload it into any PC board place, I use GLC PCBWay. They're just very convenient. Their price point is good. And then once you upload the Gerber files and pay online, they'll ship these to you within a week or two. And here you go. These guys are really 2 smart guys. This ZVS is ready for building a Tesla coil. And I like how they built this one because they put the values and the parts on the board. So this is your parts list. You could just say, oh, I need a 10K resistor. Oh, I need 2 of these diodes. I need this 150 nanofarad capacitor at a 2 kilovolt rating. So this is nice. This has everything. If you want to screenshot this, order the parts, go to their site and get their Gerber files in your Golden. If you guys have questions about this, email me. If you don't have my email address, I'll throw it in the chat. Glad to help. So here are the parts. The only thing that I didn't understand was if you look over here in the corner, these 2 white towers look like they're cement rectangles here. Those are 10-watt resistors that they want, 100 ohm resistors. 10-watt resistors do not fit in this little space. So it looks funny, but that's because 10-watt resistors are too huge. I'm also doing something here. If you see here, I'm winding the wire and then I solder it. I got a really cool tool for this. So when you're coiling, if you want really good ideas on how to coil and combine things together, go to on YouTube and look up wire jewelry makers. And they have all these little cool tools to make jewelry out of wire. And so I'll buy one of those tools or two. Yeah. And then you can, so what I do is I connect everything first. And if everything works after I wound it, then I solder it. If it doesn't work, then I just slide it off because it's coiled on.
That's a good process. I like that. Thank you.
Yeah, thank you. So I'm just going around what I'm working on. At the top corner here are 2 pieces of graphite I pulled out of an old motor from the thrift store. I'm going to be building diodes out of that. I'm going to be running some experiments on quartz and high voltage. Up the upper left-hand corner, I'm winding a ginormous globe. These over here are 1-inch solid spheres of nylon. I'm looking into warming these guys up to a certain point and then putting a high voltage negative on the top and a high positive voltage on top and a high negative voltage on the bottom. And I'm hoping to align all of the molecules and then cool it, and it'll have a permanent charge of electricity and a permanent electric field. So instead of a magnet having a magnetic field, if everything goes as planned, these will have a permanent electric field. And then over here, here's the conical coil that I'm winding. I pushed it up the priority list because it's so cool and I want to wind it. And so that's top of my list right there. You can see the inside of it. There's a top view. Oh, over here, I'm creating these spherical molds and then I'm sanding them and then I wipe them with acetone. If you dip a cloth rag in acetone and wipe any kind of filament, usually plastic filament, this is PLA, it'll polish it. It'll perfectly cause it to glow and get rid of all your mistakes. So, yep, get a rag, dip it in acetone. It's the nail polish remover that my wife uses. So if you have a wife who paints their nails, they're going to have acetone. And yeah, it's pretty amazing. And you can wipe flaws away of your 3D prints using acetone as well. If you just sand it a little bit and then wipe it with acetone, it'll have that positive effect. But what my goal is, I'm going to fill this with 2-part epoxy. While it's liquefied, I'm going to zap it with high voltage electricity until it's hardened. And my hope is to, again, align the atoms inside that 2-part epoxy, hopefully come out with an awesome electret, and we'll see. There's the side view of the cone. You can see how deep the grooves are. The groove's depth had to decrease because, of course, the cone decreases in width. So that's what we're getting there. There we have a nice shot of the cones as well. Here's me kind of showing you how the light goes through it and how it narrows at the top. Beautiful shape, beautiful engineering. Brian Brum, I got to give him a shout out all the time. He's the brilliant engineer that helps you with these shapes and designs. I imagine them in my head. I write out the specs, and then he helps you get these built. He's awesome.
That's beautiful. Beautiful work.
Oh, thank you. Here we go. Just please tell me if I'm going too fast, but I don't want to keep you guys till the wee hours. But here you just get a sense of how these coils work. There's certain printer settings that I set now where they're so tight that I don't have any extra. It just comes out of the printer this way. It's not easy to do, but it takes time to learn your printer. All right, so here's short stack again. It's not easy to see over here, but if you look at the coil on the left, you'll see that the hole on top's blocked. I put a ferrite core in there, and then I took a reading of its inductance. Now, when you work with inductance, usually it's microhenries. sometimes millihenries, but usually microhenries. If you look at the reading here on my LCR meter, it's 4 henries. That anybody who works with coils knows how huge this is. This holds so much magnetic energy at 4 henries, a massive amount of energy in a magnetic field. Crazy. So the core definitely makes a difference. Here's with no core. Here's just the air core, and it's 722 millihenries. So the reason why it's still a good high millihenry value is because it's so compact and it has thousands of windings. But a normal coil won't be in the millihenries. Usually it'll be in the high microhenries or low millihenries, I guess. So that really fascinated me. Let's see. I'm starting to put stuff in the, well, I'm not sure what this is. Duplicate. Okay. So I start just grabbing bolts and screws and bars and putting it inside the coil to see what their readings are. This is a stainless steel screw that I took out of a 3D printer, not a 3D, I'm sorry, a regular laser printer. And here we could see we have 1.2 henries. This is a stainless steel rod. It's 2 henries. This is another rod, 1.3 henries. I know, we'll get through this. This is a galvanized bolt, and it's 991 henries. So you can really change the values by what you put inside, and that's really cool. So we can call it a variable inductor. All right, so to give you just a little bit of scale, on the left is the circuit, the ZVS that I've been using for most of my videos, and at the bottom is my 6-inch coil, and you can see on the lower left you have the bowl shaped or the concave. That's 1/4-inch tubing. And then if you go to the right here, this is the new little ZVS board. This little ZVS board is different, not only because it's small and it can do a lot, but it allows you 2 power sources. So if you look here, so I can drill in here. If you look over here where my little hand icon is, this is where you put in the power from your variac. And it already has the diodes built in. So you just put your power in the variac straight in. You don't have to worry about backwards diodes. In the blue here, you connect it to your DC power supply. And here you're going to input 12 volts. So on the left here, you're going to do 0 to 50 volts AC. On the right here, you're going to do 12 volts DC. The cool thing about this is when you put in the 12 volts DC, it immediately oscillates. That's what's really cool. So then when you add the variac, it jumps on that 12 volts and starts amplifying to your higher voltages. So that's one cool thing about the 2 different power inputs here. The second thing that's really cool is you can just only connect the DC and swap out capacitors and swap out coil 1s or coil 2s and start swapping things out to get different frequencies. If you have a desired frequency and you're not powering the circuit up, you don't have to add the power to figure it out. You just have this 12 volts. And then when you're ready to juice it, you'll connect these green to the AC. This thing only runs in AC because of these 2 diodes are soldered in. And so pretty cool. It sounds like, Nathan, you have a question?
Yeah, I just thought that was so cool. The little 2 different inputs. That was an awesome idea.
Yes. The only thing is they made it a little bit small. You can see my components all coming out, but it's awesome board. As you'll see, I'm gonna run this little board through its tests. I think I shared this. Ian,
it looks like a happy family coil.
It does, doesn't it?
Yeah, it's adorable.
Oh, thanks. So I was asked by Ian about the specs, and so here are some specs. I like to keep the distance between the copper pipe turns to about 1/4 inch, and so I'm kind of outlining here that methodology. And then I have a 1/2 inch space at the bottom. I'm offering these specs because you'll see a picture, but you don't really know what to do with a picture. So I'll draw these specs on them for anybody. If someone wants to email me for any specs, I'll draw it out for them and send them and help them get started. Okay, so we're going to start seeing this little circuit and this little coil in action. And I forget what order these are in. Okay, I'm going to add DC first. So look at this DC. This is huge. This electrifies the whole room. It's so powerful. It has like a really thick hush, like a shh, and it has no crackle or anything in it. But yeah, pretty amazing. Now this is roughly 40 volts DC. And I'm going to be running between the ranges of 8 volts to 16 volts. And I'm sorry, 8 amps to 16 amps. Sorry.
It's so pretty.
And what's really cool is that little tiny circuit board you saw, that little coil, it pumps out these huge volts and amps. Huge, huge.
Yeah, it's incredible. And you said some of them have that haze around the spikes or the arcs, and some of them don't.
So when you see the AC, you don't have that blue haze like you can see right now.
Oh, it's the AC.
There's not distinct streamers, they call them. But this is sort of a fluffy ball. Now, if you look deep inside, and Nathan pointed this out, they do swirl. But the DC, this is pure DC, by the way. This is not my normal setup. And what they call this is quasi-continuous wave. Sorry, I spilled my water. Quasi-continuous wave Tesla coil is what they call this. And now the addition of more amps only makes the center brighter. They don't really make it bigger, if that makes sense. It just makes it thicker yellow in the middle as I add amps. 8 to 16 amps. Let's see here. And let's see. I have 3 videos of this.
You can see it. You're increasing the amperage, and it's like, but it's not reaching any farther in terms of the arc.
Exactly.
It's crazy. And then Nathan already proved that there's sacred geometry being formed if you have that floating on a free coil, just with its resonance. It's like making those patterns.
That's a really good point. I'm gonna have to start screenshotting based on that good idea, Ben, and see what kind of geometry I can pull out of it. And my guess is that it might give me some insight in building different geometries for my coils. So thank you for that.
You know what you should also do is when you do that experiment, do a time or exposure so you can see the lines between, so you can see the shapes a lot better. You know how they do the exposure between shots?
Yeah, I'm just writing that down. It's a great point. Slow exposure.
Yeah. And then you can also do slow motion as well, but those cameras can get expensive.
Yeah, I appreciate that. I'm gonna look into that because it's tough to even get it filmed the way I have, and you can focus it. It's in the dark. It's this crazy moving object, and yet it comes out pretty clear.
Yeah.
So here's a 12 volts, 160 milliamps. When I hit the 12 volt side, boom, I get the frequency. So it's just oscillating now, and now I'm gonna juice it with the AC. This is where I pump it. Now it's going to show 50 volts, but I fried this digital display. It's really 30 volts, not 50. Now here's the conventional output that you guys are used to.
Wow.
So this little coil can really put out some plasma. It's pretty amazing.
Wow. Yeah, that's dangerous. Holy crap. I would have been like, whoa. I would have ducked behind the counter with a helmet on.
Ben's little cute coil didn't turn out so cute, huh?
Yeah. It's a little intense, man. That's like, whoa.
That's really awesome.
It's
that is
intense
cool.
for a little dinky coil.
Look how small it is too.
And so here I'm using
Wow.
a different ZVS, just to give you an idea that each ZVS has a different kind of output.
Oh, or is that because it's changing the frequency?
So it's going to handle the resonant frequency different as temperature changes, as resistance. There's a lot of factors that do little tweaks, and so it affects the output.
Okay, so it's not just like one thing.
No, it's not just one thing. Here I'm using the dinky little circuit again. Kind of want to show you what it does. Okay, so here I start. This is bismuth. Here's where I start electrocuting things. This bismuth has a ground. I grounded it, so the AC input starts heading outward, and then it makes a bend right into the bismuth. To be honest, I took the bismuth out and looked at it closely. Nothing happened. There was no changes. But it was worth experimenting on. I'm gonna do a couple more of these.
You get superpowers or nothing.
Yeah, exactly. Here's another grounded. So you can kind of see my messy lab in the background. You can see it's pretty cool looking, but didn't really do other than just an interesting display. But there's some sort of art, a kind of artistic side to these.
Definitely, I'd say. And they seem to, like Nathan discovered, form like fractal or sacred geometry, fractal patterns of some sort.
Right. Look at that. The bismuth is not grounded, so it doesn't even know it's there.
Oh, that's so cool.
It's invisible without the ground. Now, this is one of those geodes. This is not grounded. So you saw that the electricity ignores bismuth. These ignored everything that wasn't grounded, except for this.
Oh, wow.
This is not grounded yet. It's pulling in the amps. It's pulling in the plasma. I have no idea why it's doing this.
Oh my.
I've done all kinds of objects and nothing does this, especially not grounded. There's some sort of conduction going on in there, and it surprised me, honestly. So I'll be playing with geodes more now that I know this.
Yeah, that's cool. That's really neat.
Thanks.
Well, that's cool.
Yeah.
I just threw a fluorescent lamp inside a tube to hold it up, just playing around. But I thought I'd show some of my fun experiments.
So, I like the change in color. It's more pink or magenta colored.
Yeah, it does. It'll turn yellow. It's pretty interesting, and it'll also, if you notice, gets a little fuzzy. The reason for that fuzz is that it becomes more conductive, and so then more electricity can run through it. So it acts almost like a wire when it's fuzzy like that. Pretty cool.
Be honest, you're working on lightsabers.
Oh, that would be fun.
I mean, he's got the pink one and the yellow one and the purple one.
Watch this right here. This is pushing atoms out to this level right here. But you can't see it until I start adding amps. There it is right here. Sorry. It starts spraying electrons against the screen.
What kind of lamps are those? I've seen them before. They're really cool.
It's a neon. I'm sorry, not a neon. Oh boy.
Fluorescent?
Not a fluorescent. Incandescent.
Incandescent. That's okay. Yeah. I was thinking about ordering something like that. I've seen them before.
And I'm just putting it next to the coil. I'm not putting any electricity through it.
Yeah, it's just wireless induction or whatever you call it.
Yes. All right. Nice. So let's see what it looks like connected to a ground wire. We're still working with short stack here. Now this surprised me too, because it's almost a flame. And my other coil didn't do this when I grounded it. It's
Yeah, it looks. Wow.
Look at that.
It looks different, like a flame, like you said. Like that's
Yeah.
crazy.
All those amps.
It's pure
Yeah.
amps. Yeah, that's like up to 16 amps. And not any of my coils can do this. That's what surprised me about this little coil.
Well, you have a tendency to amp us up, so I'm not surprised you amped up your coil.
Oh boy, dad joke. Good dad joke. All right. I'm gonna play with this for a little bit and then we'll go to something different.
Great work, Sean. Great work.
Thank
Yeah.
you.
Everybody's loving you in the chat.
Oh yeah.
Thanks, guys.
I thought I was the only one frying things to find out. Here it is. Sean has the secret life he's doing over there.
Yeah, I swear he's working on lightsabers. He's gotta be.
I'm so happy that you guys are interested. It's a lot of fun to share what I'm doing in the corners of my lab.
Yeah, this is all really cool.
So yeah, I'll have to try to figure out, because here again, I'm just turning it down to its lowest voltage. I think I got it down to about 15 volts and it still did this flame action.
And I just want to point out real quick, at this point, normally Nathan, I think, mentioned before, like most people doing these kinds of experiments, their circuit would just fry out. And
Yeah.
here you are doing them over and over again, like Nathan, right?
Right. And I'll show you some infrared that everything's cool. Everything is cool to touch. I don't have a fan running. It just shows you the efficiency of this little coil, the efficiency of reaching resonance.
Right.
Pretty amazing thing. Pretty amazing stuff.
And
Yeah,
when you understand.
Our
I'm sorry,
Tesla
go
coils
ahead.
don't blow up in the first 5 minutes.
Yeah, and you won't find anything else like this on YouTube because people just I guess I'm starting to see don't understand the resonance aspect,
Right. So did you like my beautiful good point. Thank you, Ben. Did you see what happened over there to the right?
No, what happened? Oh,
look at that.
Yeah.
Oh,
a meltdown.
Yeah. So there's an imperfection. Think of a water balloon, and not connecting the water balloon to your faucet, but connecting it to a fire hose. And when you turn the fire hose on, you're able to fill the water balloon quickly and tie it off without it breaking. That's an analogous of what's going on here. I'm pushing so much pressure into this little coil. If there's any imperfections in my epoxy, notice on the right, look, there it goes. It blows a leak. And so now you're getting 75,000 volts on top and 75,000 volts out the side. Now, when it comes out the side, that's not desired. That means now I'm disintegrating my coil, and bummer. That's a bummer. But I'm going to still do a couple more experiments with it as it is disintegrating my coil. This was that glass ball, if you remember, I was playing with a couple weeks ago. And yes, it looks pretty on the lower right, but it's slowly eating away the coil. But I think it looks cool still.
Yeah, it's neat, but you could tell it's destroying itself.
Yeah, you can tell it's eating itself up. So we'll watch it eat itself up. I think I
like your work with the resin, by the way. How you encase the coils in resin. I have to talk to you about how to do that with my coils, because that's a great way of preserving them. Yeah,
thank you. Will do. So I cooked up some AC, and the mistake on the side is actually looking kind of cool. It almost looks like a feature and not a bug. But this little coil, I'll tell you. Okay, now when it's hitting the concave pipe at the bottom, that's really bad, okay? Because that's now feeding back into your ZVS coil.
Oh, yeah, it's hitting the bottom. Yeah, it's hitting the coil.
Yeah. And so, rule of thumb, don't do this. But I had to. It was way too cool.
If I saw that in my lab, I probably, honestly, I would have ran or hit it with the fire extinguisher.
Oh, that's funny. here's the hole that blew out. Yeah. So if you see the epoxy here, there was an imperfection right here, a couple little bubbles, micro bubbles, and it just blew right out. So bummer. It's not completely ruined. I can still do some experiments, but I'm quickly winding a new one because I want to put stuff in the middle and do some measurements.
Sean, that's your breakout line, isn't it?
This right here.
Yeah.
Yeah, that's my breakout line.
So it blew out right to your breakout line?
Correct, right here.
Ooh. I wonder if you can carve that back just a little bit and re-put in some epoxy there.
You know, it's a great idea. When I've tried it in the past, it just blows right out again. The water balloon fire hose analogy is once you blow it, you blow it. But I'll try drilling it out and cleaning it up, sanding it, and putting some epoxy because it's a good idea.
Well, it depends how well the epoxy, combines with already set epoxy.
Yes, my problem is it's always weaker, not as strong, and then it'll find the weakness. Like you saw, it found a bubble that's probably microscopic and shot through it. Okay, so you had mentioned nothing gets hot. So this is as hot as it gets. So here's a ZVS board on the left. Here's short stack here with its needle, a little hot. But when it's white is when it's 121 degrees Fahrenheit. And then the blue here is 79 degrees. So the tip here is still just warm. Here are the two donut-shaped coils. They're called chokes. What they do is, as I'm pumping in so many amps, the amps can jump high and low, high and low. So these two guys choke the amps to make sure the amps go consistent. And so everything runs smooth. And then these are the load resistors. These are the 470 ohm resistors. What's interesting is the MOSFET is here. MOSFET and MOSFET. They're so cool you can't even see them. Now, Nathan knows how hard it is to keep your MOSFETs cool. Oh boy.
Yeah, they must be running really efficiently.
Yeah,
wow.
it's crazy. All right, my silver wire. It came damaged, so I had to wind off the broken parts and weigh it, and they're gonna pay for the lost winding because according to my calculations, it's 55 cents a meter, and I have 7,119 meters. I have some special plans for these in the future, but I thought I'd get you guys at least interested what I'm going to do with the wire. All right, here's my acetone trick. There was some flaws in my 3D printing, so I'm sanding them and then acetone smooths them out. Okay, here's my miscellaneous stuff, guys, and we'll be done here. Thank you for being patient. I'm going to be building electrets. I'll just leave that for now. So I wanted to share a before and after of how we use the ZVS coils, as Nathan presented earlier. The top are how they come from Amazon. The bottom, I remove the capacitors, and then they're set up to test with. So I thought I'd just share that before and after.
Oh, real quick, Sean, have you ever used one of those cheap $10 ZVSs in order to run a Tesla coil?
This one here?
Yeah.
They're so finicky. I want to throw them out the window of a moving truck. But I have gotten them to work. The ones on the left is very, very good. It's easy to work with. Yeah. Thank you for asking that because it's a good question. I pour in all my experience and skills on the one on the right, and it's still a pain. So as Nathan pointed out, he had a 4-inch diameter PVC pipe. Here I'm using a 3.5-inch diameter PVC. You can see, so like Nathan said, he puts coats and coats of urethane. This is 34 gauge wire. It's 7 inches of windings. The total PVC is about 8.5 inches. And you'll see this really cool effect to where as you add urethane, it sort of blends and you can't see the windings anymore. So I thought that's interesting. If you guys want to screenshot this video here, I put down the specs of the primary coil below, the specs of the top above. You can also use the specs of Nathan's. Both of these are very hardy and tested, so you can't go wrong. And there's plenty of ways to go wrong. Here's the top view of using the Amazon. Here we're running AC, so you have the diodes here up in the corner. And then if you're running the same ZVS, but you're doing DC, then you want that little switch here. And that way, when you turn on your power supply, you can boom, flip the switch. It'll shake up the ZVS here and start it to oscillate. So that's necessary. Here's that little winding winding tool. When I don't want to solder things because they're not permanent, I'll just wind wire with this little tool and it put my circuit together without soldering. This tool is pretty awesome. When I was showing you guys the one wire power and that really cool setup where I had the potentiometer adjusting the Slayer exciter circuit, here it is. This is the Slayer exciter that I used in the videos. And here are all the measurements. So it's pretty simple. A resistor, a potentiometer, and a MOSFET. Capacitor is optional, but here you go. And of course, you have your coil 1 and coil 2. Here's what it looks like if you actually build it. I don't know why that's there. Oh, okay. So look at these guys. It's in the printer right now. It's a pyramid at the golden ratio. I'll be winding a pyramid at the golden ratio, and I'll be sharing how that works in my next presentation.
Nice.
Say again?
I said very nice. I love the pyramid.
Yeah.
Thank you. Hey guys, if you want still files, email me or message me on Facebook. Everything I do is open source and whatever you'd like to do. So how do you take hundreds of thousands of volts or 10,000 volts and drop it down to, let's say, 12 volts DC? Well, you're going to either fry your resistors or your resistors are going to eat up all the power. But if you connect what are called fractal capacitors, this is what this setup is a fractal capacitor. What you then can do is step down, let's say 100,000 volts down to whatever voltage that you want. And you don't have to worry about losses because there's no resistors. I'll be building this when I build my electrics and my high voltage DC experiments. I will be showing you guys how to do that. And you can actually take static electricity, drag your feet on the floor, touch this circuit, and it'll step down to 12 volts DC, and you'll be able to run whatever you want to run. So that's what's cool about this. So it's on my now to-do list, and I'm always doing nerdy stuff like this. This is the bottom of a VCR plate. It's steel. And so I'll write down my measurements right away that I'm working on. And then I'll use a little bit of alcohol and a rag to clean it up. I don't know if you guys do stuff like this, but I wish I knew little tricks like this when I was building my lab. But so I like to share these little goofy tips. So yep, clean it up and then start over with your experiments, and you don't have a stack of paper and notes. So bismuth, I don't want to get too long tonight. So I'm practicing seeing how it adheres to mica under different heat. Now I need a torch for this, a proper torch. I was using this torch lighter. It will melt. And here you see some mica. I'm just playing with heat, mica and bismuth right now. And so nothing fancy, nothing special yet. Here I'm heating up with a candle, real high tech, but you can see how it sort of spreads over the mica. My goal is I want to try to build some bismuth capacitors. So that's coming down the pike. So when you saw all of those different coils that I'm going to be winding, the spheres and the cylinders, here are the molds that are ready for me to put them in epoxy, and you can get a sense of what's on my board. Here we have the nylon sphere that I'll be winding, and here is when I built short stack, just like that. Put it there, and there she's ready to go, and that's it. Anybody have any questions, comments?
Just
I don't know if I'm doing
thank you
this
for your
right.
presentation. I really appreciate it when you give your presentations with your coils. They're very impressive. Everything you do from the frame down to the last detail of the coil is always accounted for. You are meticulous, sir, and
Thank
I think
you.
that deserves a well-rounded applause.
Oh, you're too kind. Thank you so much. I appreciate
So-
that.
I have a question for you. It says preheat your resin before you put it in. Is that something that you would do, or right here?
I've never done that before. That sounds interesting. I know that the chemical reaction heats it up pretty hot. So when you first mix it and then you vacuum chamber it, and then vacuum chamber it a couple times, you'll see the bubbles come up. And then I'll pour it into the form, and then I'll vacuum chamber the form a couple times until I pretty much get no bubbles. And right around that time, around the 45-minute mark, it gets really hot and viscous, very thin. And then so whatever bubbles are left are usually pushed out at that time. But warming it up before I use it, it's definitely worth looking into.
Okay, and then because you also wrap the coils in electrical tape before submerging your resins for a better dielectric breakdown protection.
I'm sorry, say that again.
Sorry. It says you can also wrap the coils in electrical tape before submerging in resin for a better dielectric breakdown protection.
Oh, that's interesting. I can, but it'll look ugly. I really like the clear epoxy because it looks amazing. And I know that's probably not good on the functional side, but it's kind of my joy is to make it pretty as well as, and you're right. If I did add layers of electrical tape or really any insulator, it would increase the insulative quality, so I wouldn't burst out of the sides. But that's kind of part of the fun is to use the clear epoxy.
Okay. You should do. Sorry, Sean. Do you impedance match your coils? Your ferrite cores?
It's a great question. No, I don't. And you can see it in my on the O scope when I'm running the AC. What'll happen is you start seeing these reflections, and those reflections means I'm not impedance matched. So it's definitely something I'm thinking about because I'm losing power that way. And so when you hit resonance and impedance match, you're really incredibly maximizing your power output. So that's a good point, and it has been in my mind as I've been trying to tune these.
Okay, it says you might trap bubbles in the electrical tape. Another comment. It says, Sean, you're becoming a god. You're doing very well.
Yeah. God of Thunder.
I appreciate that. Little G, I hope.
Yeah, little G.
There you go. I take that as a big compliment. I appreciate that so much. I'll take it as a guru. That means a lot. Thank you.
Yeah, nobody's doing what you're doing or is even close.
Appreciate
and let
that.
alone understanding, how, to achieve. that level of, like coil magnification with, just a small little tiny coil.
Yeah, thank you. It's been a labor of love. It's been really fun. And I was really glad that it blew out the side and you can see it was melting, because that's the 99% of pushing through and failing. And
Mhm.
now you're seeing that I finally can do it. And I know you had that same sort of endurance in Ben and you building the rodent coil and getting it to function like it is today. And then
Sure.
pretty much everything Nathan's working on, he's taking it to the next level. And that's a lot of hard work to do that.
Yeah. Yeah, we've all endured, and it's paying off, for at least a lot of us on the team so far. And I appoint a lot of that success that I've had to the Fringe think tank and the podcasts we do with some of the free thinkers that we, talk with and can share details about our research with. It really helps, and sharing the knowledge and the science and open sourcing it. It's just, we can't do it any other way. There's no like
Yeah.
this whole method of, no, we need to keep this secret because this is mine, and that's no, this belongs to everybody. This knowledge is sacred, and it's our in my opinion, my duty to bring it out to the world, and
Yeah.
I couldn't have been where I couldn't have gotten to where I am today without the Fringe think tank.
Ditto. Yeah,
So-
me too.
Guys, real quick. Sorry, I'm reading the comments. Toymaker wants us to build a test a hairpin circuit. So we'll put it on our checklist for that.
Yeah.
I know
Yeah,
Sean and I
so,
talked about it before, but we haven't gotten very far with it yet.
Right.
Also, I wanted to share Ian's work. He's been working on the one wire power.
Oh yeah.
Oh yeah, I've seen this. Is awesome.
Okay, so I'm going to go ahead and put it up now. Let me just rewind it.
Okay, this is me replicating Nathan Old Man Bill's work, which was tremendous. I saw him getting Tesla's one-wire energy transfer system, some form of radiant energy, I presume. And yeah, so I'm just using the DC input here. It's about 20 volts. That's a tuning bank for it, a tuning capacitor bank. It just really helps. You've got
Hold on real quick before we go any further. Ian, everybody wants a schematic on how you built that bank.
100 picofards here.
Yes.
And then bigger other stuff. And using Sean Caldwell's his adaptation of schematics is ZVS board, and that's a coil I had, and I just made the primary to do this test. 3D printed a top there, so I've got 4 rods so I can put in, but I'm just using one just for this test as it stands now. The rod has nothing connected to it at the bottom. I haven't looped it or anything like that. The bottom of the coil is grounded, and obviously just the ZVS is going into either side of the primary. The probe is there. It's about 10 millimeters off the edge of the secondary coil, and I'll switch it on and we'll see how it goes. Yeah, you need to have this switch here, because if you just turn on the supply, it just it doesn't trigger the circuit into oscillation properly, and it just pulls amps through everything and wrecks stuff. So the switch, it gives it that jolt. There it is. It's on, and yeah, 0.2 amps. So that's good. That's sensible. I usually get this blurry nonsense off the current probe initially, but what I will do is I will now start switching on each nanofarad. Okay, so That's 9 nanofarads there. Now, once it settles down like this, I can start to switch them off. It's totally bizarre. And it increases the frequency, obviously, but it also increases the amplitude of the, let's see, if I go one too far, it shuts down. Let's see, nope, it's still there. All right, nice, okay. Interestingly, so the current probe is on the one wire coming off the brass rod, and it is showing 180 degrees out of phase with what the probe is picking up from the actual coil itself, which is interesting. About 1.64 kilovolts there, and it's what's that? Oops, not touching the. Oh, okay, let's try that again. I hit the wire. So I'll just put in all the other stuff again. Get it back up and right there we go. It's totally weird the way this works, but anyway. I'll just show you. As the one wire, I've got a couple of fluorescents here, and they get brighter and brighter. As I reduce, I bring it down to literally 1 nanofarad. We're back to 1.64. The frequency is just under 700 kilocycles. It's about 695 or thereabouts. Moving around a little bit, but it's fine. And that's at 20 volts, 0.22 input. And as I said, there's just the 1 nanofarad is left on. Everything else is off. So I'll increase the voltage a bit here and just show you. So both the current response and the voltage response is going up, and just lit up brightly there. That's me up to, I'm at 30 volts. I'm not going to push the ZVS board because, unlike Nathan, I hate frying stuff. But look at that. This is I've only seen this until I saw Nathan do it. I have only seen this maybe once or twice online ever. And it is just so awesome to see. That is just one wire, and that's the end of it. That's the end of the wire. You can touch it perfectly safe. Oh, look. I guess that's either my heat or my capacitance that is causing more draw through from that single wire. It's just incredible. A wonderful thing. Thank you, Nathan. Anyway.
Okay, real quick right there. I just want to show you that. He's actually touching it. By the way, once you put it through the light, you touch it all day. There's no there's nothing there to shock you, nothing there to heat you, and you can plug that wire directly into another bulb and it'll light up. Just remember to do the first part of the circuit the right way and hook it to the center and not anywhere else. So anyway, I'll just show that real quick before we go any further. Hold on. Oh, so much stuff down here, Ben. I just want to say thank you to Sean for presenting, by the way. You did an awesome job, buddy. Everybody in the chat was saying, I want to tell you.
You guys are amazing. I appreciate you guys.
We appreciate you, Sean. Every time you come on, like I said, you inspire us, you teach us, you mentor us, and you have fun with us. And you're not just a colleague, you're a dear friend.
Yeah.
Thank you, guys. I really feel like it's family, and that means a lot. I haven't shared really the long backstory of my life, maybe for a future occasion, but you guys sort of arrived in a time where I really needed good friends. So you guys in the chat, Nathan, Ben, Gerald, much love to you guys. I mean, you guys have, I don't know how to say it. I'm speechless.
No, I hear you. Yeah, it's hard to put into words, but You know, I got nothing but love for you and everybody else in the team, and including the chat. The chat's part of the team, man. You guys provide us a valuable resource. And, you know, we couldn't be more grateful for some of the people we have coming chatting in and giving us such good, you know, not just suggestions, but questions and all sorts of fun stuff.
Exactly. I learn a new thing, at least one new tip out of the chat every time, and sometimes more. So it's way cool to keep your finger on the tap, on the pulse of the chat.
Yeah, definitely. And I know you've been, was it you who said you wanted to archive it?
Yeah, I can archive it anytime. I haven't really had a request for it. But if anybody wants it, then I will save it and I'll email it to them. Someone says Gibbon Sean was a drill sergeant. I'm not surprised he's an alchemical wizard today. Do you know what that is, Nathan, Ben? Alchemical?
Alchemy is what I think it is. But hey, big shout out. Gerald's in the chat right now. He was having problems with his camera and his microphone. So hi, Gerald. What's going on, man? We missed you earlier.
Hey, Gerald.
Awesome. Well, Nathan, I'm at that turning into a pumpkin time. It has been a blast, guys. I hope we can all meet same time, same channel next Wednesday, if that works for you guys.
Yeah,
sure.
Absolutely.
Awesome. Hopefully I'll have some more interesting stuff to share. You guys have a good evening.
Yeah, have a good night.
Thanks, guys. Talk to you soon. Bye.
Bye.
All right. Have a good night, Sean. All right, guys. Gerald says he'll be here, so you know what? Let's play another one of Ian's videos and see if Gerald will show up here real quick.
All right.
So here we go.
Okay, hello again.
Ian the man. Look at
so
that.
the purpose of this test was to see if there was usable energy coming out of the one-wire system. So I've got rid of the fluorescent tubes. I've got it to a usable, say, to a battery equivalent of 12 volts. So it's about 6 watts there coming out. It's tuned to resonance, and this is obviously the coil. There's the 1/8 inch brass rod going down the center, and that's just a pickup probe on the side. Okay, so from the rod we're going into so it's like a little LC circuit. That's a 470 nanofarad 0.47 microfarad cap WEMA. It's a 6 kilowatt, and that's just under a 100 microhenry inductor. So that's a little LC current to deal with the high frequency of the line in series, and the coil is in parallel. That will go into this is a full wave rectifier using MUR 8100E, so they can deal with the high frequency of the output of the coil. And that's going into a smoothing cap of 10 microfarads there. Again, it's a WEMA to deal with the high frequencies. And the output from there is going into this cap bank, and that is 2400 microfarads, 450 volts capacity. I've let it spool up to about 308 volts there, and that's the input, and that's the output of the cap bank. So, which obviously are the same. And I've got my trusty light bulb here, which is basically ready to attach to the end of the cap. So let's see what happens when I join it. Right, 3, 2, 1.
Oh, blew it quick.
I think I just blew the bulb. I did. I guess I'll need several. Let's try that again. Okay, and yeah, so 320 20 volts shoved at a 110 volt light bulb is not going to work, Ian. All right, let's try that again. So this is splitting up between the two bulbs. 3, 2, 1. Okay, one of them blue, and the other one has completely depleted.
Oh man, Ian said he didn't like blowing things up.
He fried it and found out.
Yeah, he did. 300 volts, he knew it was coming. By the way, he just got like 300 volts into his cap bank in that one wire power and filled them all up and was blowing up stuff on the other side. That was awesome. Sorry, you there, Ben?
Sorry, I had to check on a 3D printer. My bad. I was listening. No, it was awesome. It was really cool.
Well, it answers the question, is the one wire power useful to switch back to hot side power or normal power? And the answer is absolutely yes. Ian just proved that. Good job, Ian.
Yeah, great job, Ian. That is amazing work. And Ian reached out to me. He is going to be building an Abha coil, and I will be sending him a lightning thief. So, yeah, it's going to be awesome. I'm really excited to see what you guys are going to be capable of doing with that.
Right on. He says needs voltage regulation out of the cap bank. Yeah. I love the fact that he blew something up on purpose. So
yeah, sometimes you have to fry it to like you said, find out what's going on.
My favorite method, man. You know what? And here's why. We're all kind of just sitting in here in our little labs or workshops or garages or whatever, right? And all day we're doing tests and we're trying to figure out what's going where, what's happening. And it gets kind of tedious because you fail so many times. It's like this idea didn't work and then this one. And then you're like, all right, now I'm bored. So like a little kid, you just want to fry something because it's like fun to do, right? So I'll just go over there and go, all right, well, let me turn on my high voltage now. So I'll just start ripping some high voltage, feel better for the day, get some new ideas. And then start
caps.
But doing some more stuff, man. That's the way it works. You're rocking out to a little bit of AC/DC Thunderstruck, and you're like, yeah, all right, let's get this going.
Nathan's like Iron Man. I always pictured you like Iron Man in your lab.
Oh, man.
That little robotic arm that pisses you off. Tries to help.
Little robot. Oh, man, that thing would be shitting. It would be, sorry. That thing would be shooting me with so much of that foam, man.
Yeah. Gerald, you want? I'm gonna send you a lightning thief as well if you want one. Whoever wants one on the team, it's just gonna take me time to print it. That's all. I'm looking into seeing if I can get them in bulk from a manufacturer printed. Because I have the 3D file and everything. But yes, it's very simple. I'm gonna put together a few. I know Ian wanted one, and I'm gonna be sending one to Michael and Nathan and probably a couple other people I can't think of at the moment.
Joe says happy Thanksgiving to everybody. We should see Joe probably not this weekend, but the next weekend after that. Hopefully he's got all his move done and he'll come back in and we'll have an awesome time talking on Saturdays.
Oh, yeah. Yeah. Happy Thanksgiving, Joe. And we wish you luck with your move and anticipate your return.
Yeah, everybody. Happy Thanksgiving. Yeah. Here we go. Old Iron Man. That's right.
Old Iron Man. Old Iron Man builds. Hey, dude, Nathan will build an arc reactor. I just don't know if he'll put it on his chest or not.
Oh, yeah. Lulu says happy Thanksgiving. You know what? I wouldn't mind. So I'll build it in cold energy and then throw a little bit of coil around it to heat it up a little bit and see how much power I can pull out of this thing. Now, don't know that I'm going to strap a bunch of caps to my back or anything like that to get the power to pull like a Ian, but
Oh, it would definitely power some kind of super suit for sure. Like maybe an exoskeleton or something.
Yeah.
That would, yeah.
I'll just put right in the center one of Sean's Tesla coils and hope it doesn't break out on me. You know what I mean? And then I'll just shoot it out of my fingers. You know what I mean?
That's funny.
What was cool about that coil, by the way, is that it shot out in 2 different spots. So if you put 5 breakout points on it, would it shoot in 5 directions? And the reason I ask is I got 5 fingers, well, 4 fingers and a thumb on each side. Can I make those like into gloves where I can use them as high voltage gloves? So I don't know, man. You got to get up some courage for that one. You know what I mean?
Yeah, I don't. That's pressing up against a wall there that I don't like to cross.
Now, just so you know, I did take a bunch of those high voltage taser things and I hooked them all together and I lit them up between my legs, man, and I held them. The only problem was I couldn't stop laughing. Like, I don't know why. It was a crazy response. I just kept laughing the whole time, man. Meanwhile, a few inches from the boys, it was like it was ready to set fire to them, if you know what I mean.
Oh man, that's hilarious. But I feel the pain, man. That's got to be painful.
Gerald says he found something crazy coming out soon. I can't wait, man.
Yeah, like I said, everybody on the team seems to be having some kind of breakthrough, and I love it. Like it's all this knowledge is hitting us all at once. Sometimes it's a little overwhelming, but I say keep it coming. Let's hear what Gerald has to say, and hopefully we get Victor back here and get updates on his research. And then Phil Friday updates on his research, and Mike K from Faraday, all sorts of awesome stuff.
Yeah, I miss Victor, man. I really hope Victor's computer situation got straightened out because I really do miss him. So, yeah, I hope he comes back soon, man. He's a really cool guy.
Yeah, definitely. And Gerald says his computer won't start camera now, so it's okay, Gerald. We know you having on and off issues with that, and that's understandable. We'll get you back up.
Well, I have to send him a camera for Christmas, a new one, so he gets it ready to go. Oh, sorry, Gerald. I have to mess with you a little bit, man. I didn't see you on Monday. Now I didn't see you on Wednesday, so I gotta go a little bit. Anyway, guys, this is totally awesome, man. We had a really cool presentation for everybody today, and Ben, congratulations again. You really did rock it out, man.
I appreciate that. Yeah, that means a lot. Been working hard on this stuff to try to, bring it to more people. And I think this is a big step, a big step.
Yeah. Well, I agree with you, man. You're right there. So you got everything going, man. Way, way awesome. My research is going well. We're doing one wire power through everything. And if you've seen any of my videos, I got a ton of them out there now.
Yeah, you've been reverse engineering the Tesla one wire experiments and the Colorado experiment. It's very impressive work. We're all on the fringe here, ladies and gentlemen. This is the fringe science. And don't let anybody tell you that something's not possible, because the universe is more mysterious than you can possibly imagine.
That's right. And Gerald, you're getting me again. He's doing it on purpose, Ben. Look, he's got his letters going high and low again. You know, that drives me nuts.
It's okay. I appreciate that, Gerald. I really do. I look up to you and Nathan and a lot of the people on this team. Well, everybody on this team, honestly. You guys are all great, and you've taught me a lot. So I'm looking forward to learning more about your scooter idea. That is going to be awesome. But for now, I'll settle for, lowering my energy bill this coming month for the winter, while I have cracked this method of utilizing the Joule Thief.
Right on, Ben. Well, That's awesome, guys. We had a great show. I want to thank everybody in the chat. You guys are totally awesome tonight and totally on it. We had a lot of presentations, so I wasn't able to put up all of your comments right away. But thank you, guys.
Thank you. Thank you, everybody. This was an awesome show.
Yeah. Gerald said it should be done next week. All right, guys. With that said, have a great Thanksgiving. I'll see you guys again on Friday with Mike Faraday. And then we'll see if we can't get something going for this weekend. Maybe we'll do a show. I got a lot of one-wire power things to put out. And before I go, I just want to give you guys this little bit. We are checking off the list for John Hutchinson's experiments with the one-wire power and some of the crystal technology and stuff that I'm working on along with it. So I'm not to the point of anti-gravity or anything like that, so don't get all happy about that. But as far as some of the steps that he's working on in resonance and things like that, we're getting close. So
Yeah, that's awesome. It's very exciting.
But that said, guys, have a happy Thanksgiving. I'll talk to you guys later.
Happy Thanksgiving, everybody. Thanks for tuning in. We really appreciate it.